It is my great pleasure, in the name of this entire jury, to announce you that after the deliberation, we have really appreciated the presentation, of course the manuscript, you already saw the reports, and so we all have the pleasure to announce you that there will be a PhD of the doctorat spécialisé mécanique solide génie mécanique propulsion civile de l'université de Rouen Normandie. Congratulations. Just a few words about what we about our feeling about, and that will be summarized in your report. It will be in French, the report. Unfortunately, that seems to be an obligation. Well, we all appreciated your enthusiasm, dynamism during the presentation for presenting a challenging multi-scale work. You have done a lot of work, really impressive. You made selections, you made good selections. They were strong choices you made, and based on the high quality of what you've been doing. You've shown an expertise in a vast amount of topics. I mentioned the multi-scale aspect, the process, microstructure, mechanical properties, even fatigue properties. In the reply to our questions, you showed a nice maturity in expertise, really, that is very unusual after only 3 years of research, so congratulations for that. You really handle your topic, you have possibility to propose a lot of nice perspectives. So we really appreciated very much the exchange we all had with you, and would like to congratulate you for that.
Thank you so much.
Now apparently you have to say a few words yourself.
You have to read the statement.
Statement, yes.
That's it, or can I speak something else?
Of course, anything you want.
To read the statement, and then you will be able to give a speech.
Okay. In English, I hope that is possible. So, first of all, thank you so much to all the jury members, and the president of the jury, also to give me this PhD doctorate or doctorate degree. So I read this: with the completion of my doctorate in mécanique des solides, génie mécanique, productique, transport et génie civil. In my quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principles of research integrity. And as I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity in my relationship to knowledge, in my methods, and in my research. And talking about a few words, I know many of you have to leave, so just probably starting with a big and insurmountable amount of thanks to Clément and Williams. Without them, this was impossible. Before this PhD, I had never worked on such a long project. I mean, I think that's normal with my small experience. But I always felt that I do not have the rigor to have enthusiasm for the whole project for 3 years. But for the first time, I could do it, and it was impossible without them too. And as Clément said, or I think William said, I don't remember, they complemented each other perfectly. So it's like whatever I knew Clément would say no, I used to go to William, and vice versa. So thank you for having this complementary relationship. Again, thank you to Xavier, because without his constant support and this platform at GPM, it is again impossible to continue this research. The facilities that they have, and the thing which I think has helped me most in my career is to be able to do all the experiments myself. It's not like I have to go to someone and try to do it. So this helped me understand everything in a much bigger aspect. Thank you so much to Eric's team, Sondine, Lydie, and everyone who helped me to get results. It is a big help, and thank you so much. Also, John Philip, you also helped me a lot on CM analysis. And I think at the end, my parents who are on the video call, and sorry, maybe it was them who were talking, and my wife. I think my wife has been the source of inspiration for me clearly, and she has made wonderful some Indian dishes for you to taste. So I hope you enjoy them, and I really, at the end, I want to say this as I couldn't have possibly done this without my wife. So, I think that's it. Thank you.
So it is my pleasure today to welcome you to the PhD defense of Shubham and Sanjay Joshi. And the topic of the PhD is the investigation of the link between mechanical properties and microstructure in nickel 20 chrome alloy manufactured by laser powder bed fusion. And the jury has selected me as the president of the jury. And my name is Utsima. I'm from the University of Louvain in Belgium, and I will now introduce to you the entire jury. So we have two reporters of this PhD, and the first reporter is Cécilie Duhamel from l'École des Mines de Paris, professor. Then we have Professor Nicolas Santier from the INSA Rouen which is right here. And then we have Jean-Philippe Cousini from the University of Créteil. That is there. Then we have, here. Alice O is a researcher at the INSA Rouen. And here, Eric Hugues, professor that's at the University of Caen. Then we have the members of the supervising committee, and the main supervisor is Clément Keller, who's there, and William Lefebvre. So Clément Keller is from the École nationale d'ingénieurs de Tarbes, and William Lefebvre from the Université de Rouen. So now you know everybody. So let's start with the PhD defense. Shubham, we're listening to.
So good morning, everyone. My name is Shubham Sanjay Joshi. And first of all, thank you so much to all of you who joined me in person to attend my defense, and also to a lot of people who are joining on Zoom. Also, a great thanks goes to all the jury members who agreed to review my manuscript and also allowed me to defend my thesis. Big thanks goes to again Clément and Williams for the supervision of my thesis, and also Xavier to give me this opportunity to work for 3 years in this wonderful lab. So talking about my defense here on the topic which I've been studying for last 3 years is investigation of the relationship between microstructure and mechanical properties of nickel 20 chromium alloy fabricated via laser powder bed fusion process. It's a part of NICROPA project funded by LabX EMC3. So we're very grateful to the funding. So starting about the defense, I mean, talking from an engineering perspective, additive manufacturing allows to create designs that are theoretically impossible with traditional manufacturing. This gives companies a competitive advantage so that they can not just create their products better, more efficient, but also appealing and unique to their customers. There are several processes, which exist under the tree of additive manufacturing, depending upon material to be fabricated, type of feedstock, source of energy, and so on. But for metals, selective laser melting or laser powder bed fusion process has been extensively used in research and industry owing to several advantages, and will not get into the advantages because I only have 45 minutes. But in general, you can see quickly the schematic diagram of laser powder bed fusion. So a recoater spreads the powder, on the bed, and as you might have seen the video, the laser interacts with the powder, melts the powder depending upon the CAD model, and the process is repeated until the final product is formed. As the world moves away from traditional manufacturing and goes more towards additive manufacturing, there are several manufacturers and industry and companies deploying their footprint in this industry or in this field, and you can see several different applications in past few decades. And if you look at the market size prediction for next 7 years, in 2030 the market size is to be predicted to be more than $11. So it's a huge leap for any industry to go there. And if you look at the current values, so to make this leap comfortable, the most important part that industry needs to understand is to achieve, let's say, the mechanical properties which are desired to their customers. And to reach there, the mechanical properties, it is very important to talk about mechanical properties that we have. So this wonderful review that I show here, it's yield strength versus elongation map for several different alloying systems fabricated with additive manufacturing or traditional manufacturing. And just as an example, if we look at this yellow domain, it is additive manufacturing steels. And what we see here is a varied varied mechanical properties that we could achieve for steels with processing of additive manufacturing. So certainly there needs to exist a relationship with processing parameters if you have to reach these mechanical properties. But fortunately or unfortunately, this link is not direct, and there is a huge pillar which stands in between is microstructure. And talking about complexities of microstructure in additive manufacturing, and this is one of my favorite images which I came across during literature review, and I have used it extensively in my manuscript as well. If, as an example, if we consider LPBF 316L stainless steel, we see that additive manufacturing generates multi-lens scale microstructure in terms of crystallographic texture or morphological grain structures. Then down the lens scale, we have fusion boundaries, cellular structures because of rapid solidification, which is associated normally with laser powder bed fusion process. Down the scale, we see these dendritic cellular structures in detail with dislocations entrapped on the walls. And finally, at the lowest scale in nanometers, we see these second phase particles or precipitates or oxides. So having researched for more than a couple of decades now, researchers are still trying to find the answer is which of these multi-lens scale based microstructural features are responsible for mechanical properties. So talking about the highest lens scale, which we discussed, literature review of nickel 20 chromium, fabricated with LPBF, we see that crystallographic texture and grain morphology could be associated with process parameters. So if we change process parameters, we can see the difference in texture, grain morphology, etc. And if we look at the engineering stress strain curves of the two differently processed alloys, we see there is a difference. So certainly there could be an impact of texture. Moreover, this is LPBF 316L and it's a bit complicated, so you might not, you could not look at all the images, but the takeaway from this second image is the texture or grain morphology also depends when you change the building orientation. So if it's vertical, horizontal, and it also has a lot of influence on how these building directions are oriented with respect to loading directions. So at the end of this slide, could we consider that it's effect of texture or grain morphology on mechanical properties? Well, the question is still open. Talking about grain morphology, this is a Hall-Petch relationship graph, so a graph between yield stress and inverse of square root of grain size. And what we have here is for nickel 20 chromium alloy fabricated traditionally and for nickel 20 chromium alloy fabricated with LPBF. And the slope of these curves explains the grain size dependence on strengthening. And what we see here is it does not depend how the nickel 20 chromium alloy is fabricated. We see the same slope. That means we do not have different grain size dependence here. But if we consider that with laser metal deposition of 316L, we see for the same kind of graph, yield stress versus inverse of square root of effective grain size,
we see that the slope changes for differently fabricated, let's say, samples of the same alloy. So that means there is an influence, of grain size. So can we generalize here that, okay, maybe it's a process, it is associated to process parameters, or is it associated to process or material? Well, the question is still open. This is an interesting research. So what they did is they tried to modify the Hall pitch relationship and tried to use cell size to predict the yield strength of LPBF 316L, and then compared with the prediction of grain size and experimental value. And well, it seems that it's a good match. But when the researchers tried to replicate or reproduce this data with LPBF pure aluminium, we see that with cell size, it's a clear overshoot. So now, again, we have the same question. Is it process based? Is it material based? So there's still an open question. So and we have so many more microstructural parameters that we can talk about. So just to summarize, can we say that it's an effect of texture or dislocations or precipitates, LPBF building direction, cellular structures, grain size? Well, it is just the tip of the iceberg, and we have many more problems to come. So just to try to avoid, this complexity and difficulties, we decided to employ a simple nickel 20 chromium binary alloy, which has a simplified microstructure. So if you look at the phase diagram, 20% weight chromium here, it is theoretically a monophasic alloy. It forms a predecessor for nickel superalloys, having some applications in the high temperature industry. And the advantage for this is not as complex as superalloy as well, because it is monophasic, so it's straightforward. But another reason for choosing this kind of alloy is it has planar slip, so it has strong propensity to avoid dislocation, annihilation, or cross slip. So choosing this alloy, we focused our research objectives to play around between this link, the microstructure and mechanical properties, and we could formulate 4 important objectives. The first one was, what is the contribution of microstructure of LPBF, microstructure, on yield stress? What is the contribution of same microstructure on strain hardening behavior of LPBF nickel 20 chromium samples? Finally, influence of LPBF microstructure on cyclic properties, and at the end, higher temperature tensile properties of the LPBF. But well, I only have 45 minutes. I wish I could talk about all the objectives, but here I'm just going to talk about the first 2. These are the contents. We'll start with initial microstructure, mechanical testing, and the first 2 objectives, and finally conclusions. So we will discuss about the first chapter, initial microstructural investigation. Before going for initial microstructure, it is important to understand how was the powder, how the powder was acquired. So we acquired the powder commercially. And the powder composition in weight percentage can be seen here. So 20% chromium was desired, and we have 19.9. Unfortunately, we have some trace elements in iron, silicon, manganese, and aluminium, but the weight percentages are quite small, and the balance is nickel. The parameter optimization for fabrication of LPBF samples was done before the initiation of my PhD, so I was not responsible for parameter optimization. It was done by Dr. Maxime Lelievre at CRISPR, and these parameters led to highest density and least relative porosity. So the samples that we fabricated are fabricated in the vertical direction, as seen here in cylindrical form. And one of these samples, on the right, you can see X-ray tomography images of one of these as-built samples, and we can see some porosities in blue. And they have average size of tens of microns. But having said that, we still have in general, the density of the alloy, or of the sample, more than 99.9%. We can also see the Archimedes porosity value to be 0.93%, and SEM-based porosity to be 0.25. So looking at the initial microstructure now of LPBF nickel 20 chromium, this imaging has been done in SEM ECCI, and the building direction is upwards, and we see typically formed fine and heterogeneous grain structure. If we look at the grain orientation map, we see the melting pools like this, in this orientation, the building direction going upwards, and the maximum intensity to be 2.6, which means that this parameter set does not induce a lot of crystallographic texture, but we can clearly see some morphological, texture. Talking about another aspect of microstructure, when we magnify, we see these different colonies of dendrites or dendritic cellular structures, and there are several names which will be used in the presentation, but they are the same thing. So this colony, these two colonies can be seen with average cell size to be computed 0.47 microns. And talking more about the dendrites or dendritic cellular structures, we can see these structures here, and we can see some oxides on the walls, and we also see some dislocations going through the walls and also crossing these dendritic structures. So because we're really interested in the dislocations which are formed in the as-built structure, we decided to investigate in detail via bright felt stem. Again, the building direction can be seen upwards, and it led us to discover or to see we have stacking fault tetrahedra, dislocation loops, dislocation dipoles, and planar dislocation glide in terms of dislocation subfeatures. Not just this image, this is just an example of an extensive analysis that we did, but using many images, we computed average dislocation density in soft zones to be 4 into 10⁻⁷ per millimeter square, and this will be used in the modeling in the following slides. And to have a good understanding of how LPBF microstructure changes, it is important to have a look at how the cast or traditional alloy looks like after recrystallization. This is recrystallized nickel 20 chromium. So we see annealing twins, huge grain size, which can also be seen in the grain orientation map. So twins and huge grain size with maximum intensity to be 7 or 7.1. And the ECCI contrast shows us that the recrystallized sample is almost looks dislocation free. Well, it has some dislocations, but it's the dislocation density is assumed to be quite small. So as of now, we can say that there exists a huge influence on LPBF process on the microstructure of nickel 20 chromium. So certainly it might have an influence on mechanical properties. So let us look at the mechanical properties. So on the left, you can see engineering stress strain curve for LPBF in red and black cast in black. And in the true stress, true strain framework, the same curves can be seen. There is a lot of data. It's interesting, but the most important takeaway message not takeaway because it's still a long presentation yet to go. But right now, only two important messages that you need to keep in mind is if you look at the yield stress of LPBF sample, it's more than double that of cast, and the strain hardening behavior of LPBF somewhat looks like parabolic hardening. But when we compare it with cast, we have a long linear hardening. So we understand clearly that there is a huge influence of microstructure on mechanical properties, but somehow we still don't know how and which features are connected. So, the next logical step has to be go to DM and check for changes. But here we decided to take a detour by doing loading, relaxation, unloading test. So the objective of this test, for people who are not comfortable, I'll just give like a brief background. So the objective of this test is to see the evolution of yielding surface during tension. And let's say this is a very basic illustration. If I have a sample, so normally this sample is strained to a fixed strain level, held for some minutes or for some seconds, and then unloaded. And this whole 3-step sequence is one sequence here, and then it is repeated until either necking or fracture, depending upon what you want. So here we have the sequences for LPBF in red and versus cast. Okay, and mechanically, what this test gives us is flow stress could be classified into two different partitions, which is effective stress and back stress. But before going to the mechanical understanding of these stresses, let us look why this understanding is important. So let's just imagine, and this is again a very 5th class student kind of a diagram that I'm showing here. So sorry for that. But let's imagine that there is a lonely mobile dislocation. which is sitting in black in the middle of this matrix. Now, if it has external load, it will certainly move. It will have interactions with different microstructural features. So if it interacts with short-range interactions like forest dislocations or coherent precipitates, this interaction is classified to be effective stress. So we can understand what part of flow stress is coming from which microstructural interaction. So mechanically, we can compute that if we take one sequence, okay? So this is one sequence, but here only the unloading segment part is magnified. So what we can see here is, depending upon the elastic domain, the position, the radius of this elastic domain can help us to mathematically compute or mechanically compute the value of effective stress. And another aspect of this flow stress partition is back stress. So again, this lonely mobile dislocation, if it has long range interactions with grain boundaries or heterogeneous dislocation structures, dendritic structures, incoherent precipitates, this interaction can be constituted as back stress. So here we can understand and go in deep the origin of flow stress partitions. And mechanically, using the same unloading sequence, we can use the position of the elastic domain to quantify the back stress. So having this analysis done, let us look at the effective stress versus true strain graph. So what we see here is the evolution of effective stress versus true strain is same for additive manufacturing or LPBF sample and cast. There is an initial difference, but it is due to the initial high dislocation density which exists in LPBF samples. So locally, or at least in short range, as short range interactions, we do not see any influence of the process. But when we consider back stress, again the back stress versus true strain for LPBF in red, what we see here, first of all, is the absolute value of initial back stress is much higher than effective stress. So certainly at yielding, something is happening due to back stress. And if we look at the strain hardening behavior, or at least the evolution of this back stress, what we see is it sort of replicates the parabolic hardening that we see in additive manufacturing samples. So as of now, we can understand that somehow back stress looks to be more important. And if you recall the definition, back stress meaning either grain boundaries or heterogeneous dislocations have to be involved. So again, now coming back from our detour, and again coming back to the logical step that we decided to do first, TM of strained microstructure. So this is 30% strain LPBF sample. The building direction is upwards and the loading direction is given. Again, sorry for the basic illustrations. What we see here is again somewhat stability of the dislocation cell structures or the dendritic structures, whatever you want to call them. And qualitatively, it looks like the walls have thickened. That means the dislocations have interacted. When comparing with the cast microstructure, we see a completely different picture, a completely different story. We see stacking faults interacting with some dislocations and also nano twins or twins in other micrographs. This is not very clear here. And in extensive microscopy that we did on nickel 20, the LPBF samples, we do not see any twins in LPBF. So there is clearly even post-deformation microstructure difference as well. So as of now, again coming back to the question, we can understand that yes, there is a difference in initial microstructure, there is a difference in mechanical properties, and there is clearly difference in post-deformation microstructure. And we could also narrow it down that somehow backstress, dendrites, grain boundaries are responsible. But again, the question that we asked is how much and which exact parameter is missing. So to try to answer the first question that we asked, the contribution of microstructural yield stress, the modeling that we considered here, the very basic analytical model that we considered here. So the yield stress can be separated into effective stress and back stress. Effective stress at yielding and back stress at yielding. And the back stress is further divided into intergranular and intragranular. So if we look at this slide, we can see that the effective stress, the model that we considered, the effective stress should, or for us, we believe that they are connected to solid solution and dislocation density in soft zones. And the intergranular back stress portion is connected to the grain size strengthening which is Hall pitch equation connection. And finally, the intragranular back stress is connected to the initial dislocation size, or which is the dendritic cell size that we sort of calculated or computed in the initial microstructural stage. So the highlight of this PhD, I mean the thing which I want to keep out and give as a message here on this slide is, despite having, we can look at the several parameters which are let's say, which can be seen in this equation, but the work of my PhD was to try to explain that the extracting these parameters from experiments or literature is not hard, and we can actually do it via simple experiments. For example, yield stress, which is required in modeling, can be easily extracted from mechanical loading. Initial back stress and initial effective stress can be computed from the loading, relaxation, unloading test. And this initial effective stress for cast has been used as a solid solution, because we believe at effective stress there is no initial dislocation density, or the influence of initial dislocation density is quite low. So that means only a solid solution should logically entail. Average cell size can be calculated from microstructural characterization. Same with initial average dislocation density in subzones. Average grain size and Taylor factor can be also extracted from PhD analysis quite easily. And finally, there are some parameters like Hall pitch constant, also alpha, which is dislocation arrangement parameter, shear modulus, Burgers vector can also be extracted from literature. Here, two parameters I did not mention is Fg is fraction of grains which have hard zones. So we believe that these dendritic structures are present in all the grains, so it has been considered to be 1. And Ks is a constant which depends on stacking fault energy, which can also be extracted from the literature. So solving this, or using all the values in this equation, we can actually quantify the effect of all the microstructural features. So starting from solid solution and dislocation density in subzones, the combination of this prediction is 216, and this is exactly what we get from experiment. It's a perfect match. I think I should have stopped doing PhD here. 0% error, but unfortunately life doesn't go like that, so we move on. If we look at grain size spending, it is 111, and the dendrite long range back stress is 258. So the combination or the sum is 369, which is quite similar to the experimental value. So we do not have a lot of error. And the total yield stress that we could predict from this model, again, quite matches with the experimental value. And so this shows that the model makes sense. It works. And another aspect, if we look at the contribution percentage of all the microstructural features, close to 18 to 19% is for solid solution, dislocation density in soft zones, and grain size. But the most important contribution here that we see is from dendrites. So that means a big conclusion can be laid out here is dendrites are most influential microstructural feature when it comes to yield stress of LPBF samples. But now, if you remember in the literature review, we checked that there is an influence there could be an influence from process parameters. So what happens when we change the process parameters? Do we still have dendrites as the most influential parameter? Well, the only way to know is to do it. So we tried to take a big range of volumetric energy density as process parameters. So volumetric energy density is connected to laser power. I do not have a formula here, but connected to normally laser power, hatch space, powder thickness, and the laser speed. And depending upon that, we can calculate the process parameter, the volumetric energy density, which for time purpose, I will just call it VED, because it takes a long time to say that. So we consider the long range of VEDs, and what we see here from 62 joules per millimeter cube was our sample that we have been studying until now. So this was a sample. And with range, we see that there is an increment in the maximum intensity of crystallographic textures. So till 90 joules per millimeter cube, we do not have any crystallographic texture, but with 120 and 231, we can see influence of texture. Also, average grain size also seems to be increasing with increment in the volumetric energy density. And another aspect which changes with volumetric energy density, or VD, is the cell size or dendritic structures size. And we see that with increment in the VD, we also have increment in the cell size. So apart from these values, we can actually use the same model that we used in the previous 62 joules per millimeter cube modeling. And by computing, I wanted to show a table with all the values, but it was too much data. So directly, let's move on to the graph. So what we see here is again the influence of solid solution at the bottom, the dislocation density in soft zones contribution, grain size contribution, and finally dendrites. So for all the volumetric energy density, we can see that dendrites again have the highest contribution. So irrespective of what process parameter you choose, at least in the range that we have selected by our model, these dendrites or cellular dendritic structures are most influential. Unfortunately, for 46 joules per millimeter cube, the prediction was way off. So we were 33% higher. But for other samples, we were quite, the error percentage is, I guess, for me at least, is quite acceptable. So again, just to conclude that for all the LPBF samples, we can consider that dendrites are the most influential parameter. So basically with that, we answered the first question. For yield stress, dendrites is the solution. You know a guy, dendrites is your guy for yield stress. But when it comes to the second question, what happens to strain hardening? Are these features still responsible for strain hardening, dendrites? And also could we model it? Spoiler alert, dendrites are still the most responsible factor, but let us look how. We used to answer this question Cox-making modelism, depending upon Taylor's equation and Essman and Mughrabi model. This Essman and Mughrabi model is nothing but a modification of Oruan's equation, and this depends on change in dislocation density with respect to plastic strain. So, in other words, we could see that this is nothing but dislocation production mechanism of when we go in strain, how dislocations are produced. And this equation shows us that for dislocation production, we could use different microstructural features which are responsible for this dislocation production, starting with forest dislocation interaction, the strain hardening due to grain boundary, geometrically necessary dislocations, size of the initial dislocation structures, dislocation annihilation, and mechanical twinning. But again, we saw that, and I also discussed in the initial, post-deformation microstructure is in LPBF, we do not have twinning. So for this kind of modeling, we have discarded this component. But for other parameters, if you look, almost all the parameters have already been discussed in the yield stress modeling. So we do not need anything like much more, just a couple of parameters, which is beta, which is defined by dislocation mean free path to average dislocation distance. Kg here, which is a constant depending upon grain shape and stacking fault energy, which is easily extracted from literature, and K2, which is a constant associated with the chemistry of alloys, and this is involved in dislocation annihilation or cross-link. So solving these two non-linear differential equations, we could successfully reproduce the tensile curves for all the volumetric energy density, so 2 stress versus 2 plastic strain, and using the model. Actually, there was one thing which I think I could also tell you is in this model, if you can see all the blue parameters, they have been directly taken from the experimental literature, but only 2 parameters, which is beta and L0, have been optimized by the model. So now, you can see that L0 we already have. This is this average cell size, but we decided to model it so that we can see if our model works. If we get the modeled values somewhat similar to our experiment. So solving this, we can reproduce the tensile curves, and also we could see the modeled values for L0. So we see that of course the model a bit overshoots in terms of experiments. So the ratio is from 3.3 to 5.8 for different volumetric energy density. But in general, we can see that it acquires similar order of magnitude. So using this, let's say, analysis, what we proposed here, and this work has been recently published as well. What we proposed here is we given correction factor depending upon the overshoot that this model gives. So using that correction factor, which was 0.22 actually, you can directly use L0 from experiments. So you do not even need to model optimize this value. So just beta needs to be optimized and the model works. But well, I started this discussion by saying like how dendrites or microstructural features, let's say, are associated with strain hardening. I don't know about you guys, but I think I have still not told anything. So let's get to that. So when I talked about dislocation production mechanisms and how they are associated with microstructural features, we can actually, the model actually helps us to understand this dislocation production rate with respect to individual microstructural features. So starting with the dendrites, this is the curve with dislocation production rate via dendrites, the graph, versus volumetric energy density. So the first one is 62 joules per millimeter cube. Here we discarded the 47 joules per millimeter cube, 46, because our model did not predict quite well regarding 46. So there, it seems like there has been some fabrication issues with that volumetric energy density. But apart from that, from 62, we see that the dislocation production rate decreases with increase in volumetric energy density. Now this makes sense because if you remember, with increment in the volumetric energy density, we also have increment in the dendrite size. So when the size is higher, it's inversely proportional to dislocation production rate. If we look at the dislocation production rate via grains, we see with respect to volumetric energy density, again we see the same trend. As we increase volumetric energy density, we see decrement. And also here we have a reference as cast. For dendrites, we don't because it's a recrystallized microstructure. So we can see that the cast contribution is the least. Despite having the same trend, what is also interesting is the absolute value which is given by the dendrites for every VDD. If you compare with grains, it is 6 or 7 times higher for dendrites. So here now the first indication that dendrites seem to be most influential ones for strain hardening. But finally, the third microstructural feature which is still needs to be understood is forest dislocation. So if we compare this dislocation production rates by forest dislocation versus plastic strain, what we see here is from 62 joules per millimeter cube to 120, this contribution is 0. And the cast one here, it's maximum. And somehow the LPBF sample fabricated with 231 joules per millimeter cube is behaving in somewhat in the middle. So what this graph or what this analysis tells us that with process parameters, and this modeling, it is possible to tailor the strain hardening behavior according to the desired mechanical properties that are expected. And also, if we look at these LPBF samples, we can clearly indicate and we can clearly conclude that dendrites are the most influential ones, not just for yield stress, but also for strain hardening, as given here. Waited for 3 years and already the conclusions are here. Seems weird. So talking about the conclusions, we will start with the same lovely image that and this shows how actually I liked it, not just saying it. So the PhD objective that we set for ourselves, and at least what we are discussing here, is to quantify the contribution of features on yield stress and strain hardening. And in this PhD, we could successfully do a multi-lens scale analysis for nickel 20 chromium. And we could also understand that cell diameter less than 1 microns or this dendritic cellular structures or dendrite is clearly the most influential parameter to answer both the questions that we asked. So just as a bird view to conclude in the bulletin points, combined mechanical testing, microstructural characterization, and modeling is necessary to estimate, at least for nickel 20 chromium, it seems important to estimate the contribution of AM length scales on mechanical behavior. Nickel 20 chromium, or in general nickel chromium, seems to be a good candidate to study this link. As I said, can easily avoid complexities and dislocation annihilation. Clearly, we could conclude that dendritic cellular structures, after the contribution of AM microstructure, are responsible for majority of yield stress and control strain hardening. It is possible to tailor microstructure according to the desired properties. So depending upon process parameters, if you want forest dislocation interaction or dendrite dislocation production and so on. And finally, the correction factor that we try to propose and also the modeling that we propose, I think it paves the way to include this Cox-making modelism in crystalline plasticity modeling of LPBF to understand the plasticity behavior in much more detail. And now the prospects. Now, mind you, I have no idea how long I have spoken, but the prospects are going to be slightly longer, and I'll tell you why. I could not control myself from not talking about cyclic properties. So this was supposed to be out, but I cannot control myself. And then I'll tell you the reason of why I decided to include this in prospects. So I will not go into too much detail. So here we can see we did quite a bit of test on LPBF and cast samples or low cycle fatigue, medium cycle fatigue, and high cycle fatigue in strain controlled environment or strain control conditions with completely reversed conditions. So the maximum strain and minimum strain is same in magnitude. And here is a evolution of stress amplitude with respect to cycles. So there is a lot of data here, but I just want you guys to look at two takeaways from this slide. One is if we compare the evolution of LCF in terms of it is LPBF sample, this red, and this is cast. First, we see that LPBF increases fatigue resistance quite significantly. And another aspect, now I just talked about in conclusions, is the reason that we talk so much about nickel 20 chromium is it has strong propensity towards being a planar alloy, and it avoids cross slip and dislocation annihilation, so clearly we don't see any softening here, which is a material property. But if we can see it in LPBF, we have a strong softening which happens in LPBF samples, and the same degree of softening can be seen in medium cycle fatigue and somewhat is seen in high cycle fatigue. So why? And the reason, I mean, we don't know the reason, it's just an hypothesis, and this work has been accepted with minor revisions as well. But this is what we propose, but it still needs many extensive microstructural characterizations. So if we look at the post LCF fracture LPBF sample, the bending direction and loading direction are upwards. I don't know why I did not put it. So we look at a lot of slip bands, and if we magnify on one of the slip bands, what we see here is the new cyclic dislocation walls are seen to be forming, and it does not now overlap, or it overlap, but we can see a lot of softening, so a lot of disappearance of dislocation, and also the dislocation cell structure seems to be modified. And if we look at the mobile dislocation, somehow it has the same shape or direction, same shape as the new cyclic wall. So somehow it seems that this dislocation is moving and the dislocation structures are modified. So we talked so much about dendrites and stability of dendrites, but somehow in cyclic properties, these dendrites are not stable, and we don't know the reason why it leads to softening, and that's the reason it's in the prospect. Another prospect which I would like to discuss is when we compare different volumetric energy densities, and we had a look on the contribution of microstructure on yield stress, we made a very strong assumption that the dislocation density in soft zones should be equal in all the samples, and it's a very strong assumption. The magnitude should be similar, order of magnitude, and this is what we get from the literature, but certainly it's not same. So as a prospect, I would like or any person who is interested in taking this research further to compute dislocation densities extensively by TEM to increase the accuracy of the model. Finally, we did some high temperature test, and the reason I added this in prospect is nickel 20 chromium has propensity towards forming short range order at close to 550 degrees Celsius. And if we look at the LPBF microstructure, it is already complex, and now if we have short range order, it could be even more complex. So understanding that is still necessary for successful execution or successful application via nickel 20 chromium. And if we look at the engineering stress strain curve at 500 degrees Celsius, the test temperature was 500 degrees Celsius, we clearly see the dynamic strain aging. So clearly, somehow, Poitevin-Le Chatelier effect should be the cause for investigation. And finally, I completely discarded the influence of oxides, which form because probably of the trace elements, manganese and aluminium, silicon, and so on. But if we look at these curves, we can clearly see that dislocations are looping around these oxides, and these oxides are, mind you, should be incoherent with the matrix, and still it is interacting. This is not very common, but we saw in one of the micrographs that it interacts with slip trace. And the EDS analysis of these oxides shows that there forms like a chemical segregation in terms of core and shell. So somehow, maybe these oxides could also be influential on mechanical properties. So it would be really interesting to take up as a challenge. So I end my talk here, and thank you so much for listening to me, and I would love to answer the questions.
Thank you, Joshi, for this very nice and lively presentation. I will now give the floor to the reporters for questions, and we'll start with Cécilie Duhamel.
Okay, thank you. First, I would like to thank the new supervisors for inviting me to participate to your jury and to evaluate your work. And I would like also to congratulate you for the presentation. I think it was very, very clear and with a lot of enthusiasm. And so you choose to present only a part of what is in the manuscript. I've seen at the end that you put some of the other results you get in the prospects. Regarding the manuscript, so you have chosen to write a manuscript based on articles that you published. So I think it has both advantages and drawbacks. The advantages is, of course, that you have already work published, and this is from what I understood, you have 2 papers now which are published.
Already published, yeah.
Yes.
Conference paper is also accepted, but it's not published.
Okay, so it's a very good work. The drawback when you read the manuscript for PhD defense is that sometimes you miss the kind of overview of the whole work you did and how the things are getting together, and sometimes it leads also to some redundancies on the way you write. Yeah, but actually it was clear, and it's a very good work with a large amount of experiments and analyses. So I will move to the questions. First, so you've shown that you've fabricated specimens with different size, especially cylinders in which you machine the tensile specimens. So just to be sure I understood properly, you always machine the specimens from the bars, or sometimes you use nature specimens directly?
No. For my analysis, all the samples have been machined, yes.
Okay. And so I guess you machine several specimens in one bar, one cylinder, or only one per?
No, only one per cylinder.
Okay, so you are sure to always machine them in the same part of the bar, and you don't expect any differences in the microstructures from one specimen to another that maybe you may have from the top and the bottom if you machine several specimens.
Well, certainly there will be differences in microstructure. So I think even if we machine in the same zones, still depending upon where the position was of the cylinders, still have some influence on the oxides or the cooling rate, or not cooling rate, but the inert gas rate. So it will be different, certainly. But yeah, we normally, for every testing and every microstructural characterization, we normally take a statistic. So except for TM, but for SEM and mechanical characterization, we have taken many samples, 3 samples, 4 samples, minimum. So our all the analysis is averaged. So what we see here is, it is not some abrupt nature of any one sample.
Okay, so, and because after you said that for each condition you did 3 tests to check the readability of your results.
Yes.
But if I'm not wrong, I think you don't show this in the manuscript or neither in the presentation. So you always, for example, when you make tensile test, the 3 pairs are exactly the same. Always, okay.
Well, no, not exactly the same, but with a range of 20 to 30 megapascal difference.
Okay.
Yeah, but in the In the statistics here, I mean, in the mechanical properties that I showed here, we can see this error bars as well.
Yeah, I've seen that. Okay. But yeah, I'm asking the question because after when you are using your making modeling and that you are fitting the parameters, it seems that there's one table in the manuscript when you give different beta values, and they are very different.
Yeah.
And I mean, if the curves are exactly the same, I don't understand why there are such differences in the parameters that you are fitting.
Yeah.
So, do you have an explanation for that?
So the explanation is, or at least what we have extracted the explanation from this, is whenever the beta parameter is, huge, 10 to the power 12,
Yes.
or minus, sometimes the values are minus 5 point something into 10 or 12 or 9, it means that this feature is not responsible. So if you see the formula, it's almost infinity. Yeah. So the influence is 0. So that means, and the model is based on fitting beta parameters depending upon how the two non-differential equations can be fit. So as soon as it gets the value that the whole feature is 0, it gets random values.
Yeah, after it's okay. Yeah. Because sometimes you have, you have 8 orders of magnitude between the minimum and the maximum value, which is quite huge. So,
yes.
When it's 10 to 5, you consider that it's already infinity.
Yeah.
Okay.
Yeah, exactly. So if I just talk about a bit more,
so basically that means that if you want to get even more simplified modeling, you can squeeze this term from the model for the LPBF material.
Yes.
Yes, that's your conclusion. I mean, you can even have a more simplified law for the.
Yeah, I'll just like to show this slide.
Yeah, here you are varying the conditions also.
Yes, so with different conditions, you can see that for 46 to 120, where the beta is 0, that we saw the contribution, it's to the power 9. All the values are random. But as soon as we saw that the forest dislocation interaction is working for 231, we see a finite value.
Okay, yeah.
So that means
this one was okay.
That means that the model, and for cast also, where we see higher contribution of beta, we see the value makes sense. So this is how the interpretation is made.
Okay. So now I have also questions on the methodology because you don't explain too much on which you said you have a lot of statistical data for the microstructure description. So can you just explain us on which how you perform your grain size measurements, dislocation cells measurements, which surface, how to just can you explain it?
For dendritic cellular structures or cells, what we do is we have selected for 62 joules per millimeter cube sample, we have selected 8 different locations. And what we do here, at same magnification, we consider normally one single colony. So we do not go that the colony boundary is between. So we try to get one colony. And then using ImageG, we can have an analysis of the average size. And then depending on the average size given by ImageG analysis of one colony, for 8 different locations, we have taken the statistic.
Okay, and so you do this within the contrast channeling imaging?
Yeah, the imaging, yes, has been done by ECCI, yes.
Okay, and for the grain size?
For the grain size, we have considered EPSD analysis. I will just show here. For the grain size analysis, we use EPSD analysis and we see the maximum area fraction. We choose like an average grain size.
Okay, so you use the equivalent diameter to estimate the grain size from the EBSD. Which method do you use? You have different methods in the EBSD from the EBSD data to analyze to determine the grain size. So did you consider the surface of the grain and try to calculate the equivalent diameter? Is it the method you use?
No, we directly took the information from the EBSD analysis, directly maximum area fraction versus grain size, and we took an average. So yes, we have variability of grain size clearly in the model, but we went with the average size to at least have first foundations of the model.
So just in this slide, because I have another question regarding the grain size. So you performed all your tests with the tensile axis along the building direction.
For test, yes.
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 At least for what you showed.
Yes. All the tests have been here.
Yeah. And okay, it's not. There is a slight difference on this specimen between the plane you are looking at for the grain size. So which value of the for this energy density, it's not so different, but I guess for the higher values of the energy densities, you should have a more pronounced morphological texture.
Indeed.
So which grain size do you take into consideration in your model? And would you expect to have the same results from the tensile test if you would have done the tests in the perpendicular axis?
Okay.
So there are two questions.
Two questions. Yeah. Answering the first question, what we do is as shown here, we take different slices. The first LPBF in bending direction and the cross section to see the grain sizes in different area fractions of grain sizes in different axes. So we can try to see if we have a morphological texture and if there is an average. So for other samples, also what we have done is we take an average or the highest area fraction for grain size for one axis, and then we take another axis higher, and then we take an average. So it's a bit crude method.
To be sure I understand it, that means that the grain size you use in your modeling after it's an average between the two planes?
Yes.
Yeah.
Yes. It's an average between two planes. It is a crude, again, I think method when it comes to grain size, because the aspect ratio will increase certainly with increase in volumetric energy density. So again, as I said, there is a variability in terms of microstructure, and certainly it will influence the model. But for the average, we have tried to show.
Okay, so then,
but if we look at,
if you change the tensile axis,
yeah, now the tensile axis, yeah. So tensile axis change is a long answer. So I don't know how.
First, would you expect to have the same curves?
So there will be if we print the samples in horizontally and then test in perpendicular, the loading axis is perpendicular to the building direction.
Yes.
That material, the mechanical response will be higher. We have done this. Celia Brooks works on the stable aspects. So the horizontal sample has higher response.
Yeah.
Higher each spares, higher UPS as well.
And in terms of strain hardening, you have the same thing?
No. So I think it has similar strain hardening. Yes, but I think what she worked with is with different volumetric energy density. So we could not compare it with my volumetric energy density. But I will tell you the reason that we chose not to have this analysis, and the reason that it was also because at some point we have to start first of all. So we cannot start at all points. But one of the major reasons that also come from literature is there is a fantastic paper in Matériaux, and they have what they have done is the LPBF of 316L, and what they show is when the sample is printed vertically versus horizontally, the vertical one, it has different let's say heat transfer behaviors when if you have larger area to be fabricated with laser, if it's horizontal, my bad. And if it's vertical, it has small area in one layer. So the heating cycles and the cyclic heating will be different. And when the sample is printed horizontally, it has more. The dislocation cells seem to be a bit smaller. First of all, also the initial dislocation density is higher. And if we look at the strain hardening behavior, simply the strain hardening behavior is not as good as the vertically printed, because there is not enough space for dislocations to be stored, because there is already high initial density, dislocation density. So it is this is also one of the purposes that we chose to stick with the vertically printed samples. Is when we have higher range of strain hardening, we could actually investigate it in a more detail.
Okay, so if I understand correctly, that means what you're saying is that if you're using exactly the same material but just changing the direction for straining, if you want to apply your model in the horizontal samples,
Mhm.
let's say, then you would need to, sorry, I'll start again. The different behavior, according to you, is linked to finally a difference in the microstructure, but in both things. This is what you say from what I understood. Or otherwise, how would you adapt your modeling using the same material?
I think the modeling,
using a tensor test in the perpendicular to the beginning
yeah,
direction.
I feel the modeling does not need a lot of different parameters to be included for the successful execution in different building direction. Only few parameters will change. Grain size might change, the dendritic cell size will change, dislocation density will change. So as long as you have these information, other samples, other parameters have been, have come from the literature. And also, I would like to point out here is in the same paper. Actually, I like that paper quite a lot. In the same paper, what is shown is when you print in a horizontal direction versus vertical direction, the aspect ratio of grains remains between 2 and 3 for optimized, like if the volumetric energy density is not too high. So that means we do not have a huge difference in the grain size aspect ratio. So the model might not have huge issues when when we consider it for the differently printed samples.
Yes. So you show that there is a high contribution of the solution cells, right? So this is quite convincing. You're talking about the size of the dendrites. I was wondering, but if there could be also maybe at the second order an effect of the thickness of the walls. And I mean, there's a lot of things in your walls, the dislocations. You have the precipitates, so you talked a little bit about them in the prospects. Do you have also maybe some heterogeneities in the chemistry between the walls and the inside of the dendrites, or is it homogeneous? This was also.
So literature shows us that there should be chromium segregation. Then we have seen oxides which are chromium rich. So there seems to be some heterogeneity. But when we tried to do atom probe analysis with Williams, and we saw a plain monophysics structure. But again, we were not sure if we had the dendrite boundary in between, because it was quite complicated to take the chunk out. And we also used Fib analysis to try to have, let's say, sample preparation from a different point of view to see if there is a chemical heterogeneity, but the sample also did not show. But this could also be because the contrast is difficult for chromium and nickel to be shown differently. Yeah. About the first question, yes, we analyzed dendrite wall size for 7 different locations, as I mentioned. Oh, I mentioned 8. Sorry, for 7. So yes, we have variability in terms of cell size and wall size. First, we were going for this wall size modeling. So there is anyway, there is a modeling based on let's say GNDs, or focused on hard zones. So we were thinking to go for the dendrite wall size, because we can compare the fraction of this dendrite wall size and try to analyze it with the hard zones. But finally, we decided to go with the soft zone dislocation analysis, and that's the reason we could eliminate the dendrite wall size. But certainly, it is influential parameter.
And there is also a correlation between the cell size and the wall size. I mean, the thinner they are, the thicker are the walls, or not.
Well,
you only did this for this energy density, but
yes, so the wall size has been only done for one energy density, but the interdendritic lens average cell size has been done for different densities as well. But yeah, it is, I don't know if it's correlation or causation. It seems here, but we are not sure.
Okay.
But certainly, because I feel if the walls are thicker, that means the dislocation might have, might need more stress to go away.
Yeah.
So certainly physically there should be more there. Yeah. But it's a prospect again.
And regarding the precipitates, so maybe I think it would be my last question as far as so you've shown those precipitates. I was wondering more for the fatigue part because you use two different. You didn't talk about this, but you use two batches of powders as received and recycled, and you see slight differences in terms of lifetime for your specimens. You analyzed them with the view of the porosity, but I was wondering, could there be any effect of the precipitates on the lifetime? Because do you see any differences in terms, I don't know, precipitate density, size? Did you look at that?
No, actually, chemistry was not like, a big chunk or big part of my PhD, so we could not have a detailed look on that. But certainly, I mean, logically, if we use reuse powder, certainly oxygen level would be higher. So the oxides should be higher.
If I remember
Yes. So it is a contrary effect. But yes, it is quite difficult to analyze. But certainly, what we feel is right now the most effect is coming directly from the porosities, because the effect of porosities is much higher because the length scale, or let's say average size, is.
But you don't see too many differences between both batches, if I remember, in terms of porosity. So
Yes, but also we saw a bit of scattering as well. Even if you look at reused powder, we have a lot of scattering, and new powder also a lot of scattering. So the analysis hence becomes even more difficult to like if we again have a correlation or a causation. So again, it's the same logic, I think. But yes, certainly, if I feel if the porosities could be minimized to a level which is not the first order, then all the second order, like precipitates, oxides, dislocation density might be different. This could play a significant role in fatigue. Yes.
Okay, so thank you very much, and congratulations again for the presentation.
Thank you so much.
Thank you. So we'll move to the next reporter, Nicolas Saintier, from professor at INSA Rouen. Please.
Thank you very much. First, I wanted to thank you for your very nice presentation, and for the manuscripts, and for the invitation from the supervisor's team. Great pleasure for reading your manuscript. So it's a very difficult subject, I think, because you were trying to go to the very small scale to the very upper scale, and that's very challenging, and I think it's very also interesting, and it's a question for all of us, how to link those very complex microstructures to the mechanical behavior at different scale. And that's really, I really appreciate that work, in the sense that give us some real, weight on the different aspects or features of the microstructure and how they impact on the mechanical behavior. And I think that's very both difficult and key issue for us to control these microstructures and understand them. So thanks for that, for doing this PhD. On the manuscript, I think it was very not easy to read, but very dense in some stage, because the format of the papers. So sometimes there are some limitations. So sometimes there is kind of mixed between the papers and some more information given to the reader. Yeah, it was just straightforward, the papers. So it was just the only issue with the manuscript, but it is a choice which is very efficient from a publication point of view, and I understand that very clearly. So sometimes it's hard to find the good balance between a fully detailed PhD and no publication, or a lot of publication with a not fully dense reading. So, that's a choice, and I accept it. So I have a few questions on your work. The presentation was very dynamic, so it was very nice to follow. First question will be on the microscope. I have some similar questions as this year, but I would just go back to the microstructure features that you had on the grain size. And at some stage you spoke about when you had all the morphology of your grain. This was the one after, I think. Yeah. You say that there is some morphological, you said that sometimes there is some morphology of the grain, some texture of the grain. You did morphological texture. I think the term you have been using is morphological texture.
Morphology of grains, yeah.
Say that, sorry. How do you quantify that?
Probably quantification is just the aspect ratios of grains. Could be
on different planes.
of different planes, yes.
Yeah. So how did you try to? I mean, how did you quantify that really? It's quite difficult.
No, it came from literature review. So this is not my
Okay,
work.
but on your work, at some stage in your analysis, where you have all your microstructures, you said that you had this morphological aspect. You have the morphology of your brain, which is more or less complex, depending on the BED as well. It's changing. You have the slide. I don't think
It's 31.
I did not this
Yeah,
one.
yeah.
Okay, so when you go from one side to the other one, you are changing as well this morphological aspect of your brains and the 3D aspect of the brain. So did you try to analyze that? Did you focus on that a bit? And when we think about grain size, I think that was a bit the question of Steve. Can we really put a grain size on this type of microstructure? On the right hand side, okay.
Yeah.
The left hand side,
It's a bit complicated, certainly. But again, there is an interesting. I did not use that in my analysis, but in literature review tells effective grain size also. So just to compare or to talk about probably mean free path for dislocations. But here we have dendritic cells, which also are more governing factor for the mean free path. So I think that effective grain size could not or might not be very useful for directly this analysis. Yes, we did not quantify the morphological aspect. It was a qualitative analysis to see that clearly the morphology seems to be changing. But using the average of the two, yes, there are, again, this is a very crude assumption that we can take the average of grain size in different orientations, so in XY plane and in XZ plane. So certainly there could be a factor or sensitivity in terms of a correction factor of aspect ratio, which could improve the model. But as of now, I cannot direct you towards the quantification of this factor.
yeah, because that was my point. The main free path, or at least the long range interaction.
Yeah.
If we have very flat grains with complex shapes, with grain boundaries which are in fact not related to the grain size. So we may have a decorrelation between the grain size and the physical barriers not playing a role in the interaction, and then in the evolution of the backstress or.
Yes, it is certainly that certainly will increase the understanding on grain size. So as of now, but we again, modeling was some part of the PhD, so we decided just to go with the average sizes of different.
But then now, with the experience that you have on fitting your model, the data you have in mind, do you think this is an issue in which we should dig in, or do you think that finally it's not a primary importance?
So, well, yes, we should dig in first of all, and secondly, it is not of primary importance. Yes, dendrites are still primary, and if you look at the contribution of grain size is quite significantly smaller when we compare to dendritic structures or the contribution of dendrites. So even if we have changes to the model, if it considers effective stress, effective grain size, I don't think it will supersede the dendritic contribution. So the model or the prediction will not change significantly by this understanding. But certainly to increase the accuracy, it is important to deep dive and to understand the aspect ratio, morphology, and as you said, the effective barriers for dislocation movement or for backstress understanding indeed.
So now that we are on that side, in your analysis, you have a given set of parameters that you identify or get from the literature. But I did not see in the manuscript the sensitivity analysis of each parameters, which means like, okay, how wrong can I be on those parameters? How much else that going to impact this distribution? because you have this distribution because you choose some set of parameters. But assuming we have errors or assuming we have some scattering of the data, will that be very sensitive or not very sensitive? I mean, I change completely this distribution because I assume some scattering on the inputs that I'm using.
Again, so as I said, the most influential parameter is dendrites. So it will, and the error that we get for dendrites is quite small if we see different locations. Moving on for different locations or different parameters, if we directly look at the formula, I feel dislocation density in soft zones could be a parameter which can be sensitive or which will change the model a bit or the sensitivity on this parameter. But we tried using different dislocation densities, so double or half the dislocation density that we have, and the effect is only for I think 35 to 40 megapascal. So the error is not too much, and certainly we will have an influence of parameter like grain size here and the dendrite size. So apart from that, I don't see the model will not predict too wrong if the fabrication is done properly, because for 46 joules per millimeter cube we did not have the good, I think, density, and we have a lot of porosities and the fabrication was not optimized. So that certainly had some issues, 33% error. But when the fabrication is seems to be okay, the model seems to be okay.
Okay. But it's not to be good or not on the model, like fitting well the data. In a way, we are fitting some fitting parameters at some point. It's just to make sure that the interpreting, finally, to my opinion, was a key interesting thing is to understand better the physics. So it's more saying, okay, if I'm wrong on the parameters, is the physics great questions or not? And that would have been a good thing to have it in
I'll just like to talk about 2 minutes more on this topic. So when we talked about let's say the physics will be wrong. So in strain hardening modeling, we see that for this dislocation production mechanisms, when we change the dislocation, the VD from 62 to 120, so it's a huge change. And we can, we also saw that, if you remember this slide, we changed from 62 to 120, we have like almost double the dendrite. So the error will be significantly smaller than the change that we have here, but still we see the dislocation production mechanisms, for example, is of same order of magnitude. So it will not change significantly. The physics interpretation will be there, what we are showing here.
You said the dendrites are not quite sure that are the key parameters, private parameters. Those dendrites, there are some sort of anisotropies have a main direction. They are formed during the solidification process, which means that they may have some sort of global anisotropy in that orientation. And we reduce them to a scalar. So it's a question. So my question is, do you think that this dendrite orientation play a role on the macroscopic response? And if so, how could we include that? And if not, why?
So I think I cannot absolutely answer this, but what I feel is yes, it will. I feel like there should be some influence on the orientation of these dendritic colonies. But having said that, actually I have an image from literature. This image. So this is a recently a paper published in Materials, and it's a very interesting paper. What it shows that we have different. So sometimes we see. Sometimes we see that dislocations are coming off the plane, or they are elongated, but they are not elongated. The size that between the distance between two walls are similar, and it's just the colony is rotated. So I don't think that we have to consider different, first of all, average cell sizes. We can directly take the minimum difference. So it should be helpful for this understanding. And now when you say that, will it change? Yes, it will change. And the reason why is many papers show that at the border of these colonies, or sometimes even on these walls, because of oxides or some pores or something like that, it could be it could generate or it could propagate, it could, let's say, induce nucleation for cracks, and then it could be like an intra dendritic fracture. So when we, not about yield stress, but when it comes about fracture mechanics, I think certainly it will have a huge influence. The orientation of these colonies, in which direction they are oriented. Yes.
And
If I'm not wrong, this is 316L also.
Oh,
Yeah. Yeah.
you can not on the yield stress.
Yes, yield stress. I'm saying it might have an influence. I'm saying the fracture and the crack initiation has no influence on yield stress. Like the second aspect that I talked about.
But these substructures may have impact on the yield stress as well. Also, endotropy or not?
Difficult to say. I think that on yield stress, the influence might be not negligible, but not as pronounced. But I feel they might have more influence when it comes to probably strain hardening, because when it comes to dislocation movement or probably fracture mechanics, they will have played a significantly more role, or more important role. Sorry.
All right. And so you spoke about microstructure. We did not speak much about defects. Just considering the large range, usually when you look at a range of PhDs and you put that in a map of defect, more or less you make a summarization. You make two ways of doing that, or you analyze the density, and people say, oh, it's 99.98, it's so good. And when you look at the tomography, you're scared about what you see. So you were able to control a fully dense material with this very large range of VED. I mean, you have a defect population that normally should have been popping up somewhere.
So the X-ray tomography was done only on one volumetric VED sample, 62 joules per millimeter cube. So we do not have the information of tomography and pores of other VEDs, first of all.
Okay.
Yeah. So I think that.
With the metallographic analysis or just cross section?
So can you clarify? So you mean if different VEDs might have different pore size or porosity analysis?
And density, yeah, and density may play a role as well, a bit on the behavior, maybe at some stage. Maybe not that much.
Because we have used VED just for yield stress.
That's what I'm doing.
Yeah, for fatigue we have not considered different VEDs. So for yield stress, yes, we have considered the porosities might not play as much role. For strain hardening, again, I believe that it should not be too pronounced.
Yeah,
so
the first order.
Yeah,
I agree with that. But for playing with those microstructures in a fatigue context, it's not that easy.
Yeah, certainly. It will be too complicated. Yeah, I think it will need another half a PhD to consider that.
Yeah, even more. Yeah. Just last question on the grain size and texture effect. There are some works in the literature where people have been doing synchrotron or neutron diffraction analysis, looking at the effect of the shape of the grain morphology on the local stress and comparing to numerical simulations. And when you do that, effectively, it seems that the grain morphology has not a significant impact on the mean stress, on the stress at the grain level, for some reason, which are yet unclear for me. But, so they are more or less in the direction, but that could be also a way of analyzing more precisely the local stress. For the fatigue behavior, you've been showing some slides at the end of the prospect. I found it I was very interested in that part, of course, but Just on the loading condition, I was a bit surprised to go in the HCF, in the HCF domain, being, I think, total strength control. That's where the kind of loading conditions. Why that choice, maybe? And do you think that going into a stress control loading condition would lead to different conclusion or development of dislocation structures? Because you said at some stage when I'm in the LCF, I have got a type of dislocation structures that are more or less disappearing in the LCF domain. If you had been going to a stress control test, do you think that you would have seen something different? Not for the LCF function, for the HCF. LCF, of course, have to be a question.
I have no answer. I'm sorry.
So I put it differently
because I did not consider stress control at all in my PhD.
Okay, so if I go for it, I put it differently. What could we promote under stress control that is completely locked under strain control?
So I think when we just consider stress control, then the existing residual stresses of LPBF might play some role, because in that case the maximum stress might not be equal to the minimum stress, because the residual stresses will at different locations of the sample will drive one kind of stress more than other. So there might be some differences in the stresses, and this could lead to different dislocation interactions or dislocation, let's say, production or movement. But to predict what they might be, unfortunately, it's beyond me as of now.
Do you think that, what do you expect if you have ratcheting, for example, when you're on stress control, you may have some ratcheting starting to build up, even at a very small scale. What do you think about the structures that we would be developing in interaction with the dendrites that you have? The dendritic structure, how would they play a role in the development of microplasticity in that context? Do you have some idea? Following your expertise now.
Yeah, I have not analyzed ratcheting or this part of fatigue at all.
Okay, so for the HCF under strain control, you said that the dislocation cells that you had, the dendritic structure that you have, were more or less disappearing. Did I understood well? Or?
Yes, like some parts of the cells were disappearing, yes.
Could you show it again?
This is, so you see here is, so what I said is this is a sample after LCF fracture, first of all, for LPBF 2K20 program, and we see a lot of slip bands. And if we magnify one slip band, what we see, first of all, if you can see here, it's almost like the dislocation wall here is getting thicker, and this is not what we saw in the initial state, and the dislocations here seems to be disappearing. I'll just close it. And if you look at the magnified this new dislocation walls or dislocation cells, what we see here is it's thicker but preferentially. Here we do not see any dislocations at all, and the reason is why we think this is thicker and big. It makes sense because we saw a lot of such mobile dislocations have same shape as these thick walls. So maybe it seems like almost these mobile dislocations are moving, internally to reach one region or one part of the wall from other, let's say, wall parts.
From one side to the other one? Yeah, they are building up there?
Seems like that, yeah. So we also did some EM at the softening zone. There. Okay, anyway. what we did is, and it's also in the manuscript, what we did is we were really interested in what happens to the dislocations when it is still in the softening zone. So we stopped MCF test at at this point, at 10,000 cycles or 1,000 cycles, and then 1,000 cycles. And then what we did is we took this part. So it was an interrupted fatigue test. We took this part in TEM, and then we saw many primary is a strong word, but some slip systems which are active, and then there is a dislocation pileup, and this was between two walls. So it seems like the dislocations are somehow going from one part to another part, and this somewhat helps our hypothesis or the post deformation or post fatigue microstructure. So it looks like they are moving in this direction. Oh yes, they are disappearing at one point and getting, let's say, differentially stacked up at another point, and this is changing the overall cell size. So it's let's say, it looks like the cell size is increasing, and hence this increase in the cell size or movement of dislocations or the modification in cell structures, like the combination effect or one of these or many of these, is inducing softening. This is what we hypothesize.
Okay, so I have the last one, but I don't have time. Just
Very short answer.
Very short.
Short question, short
Just
answer.
finish on that one. I think you had a discussion at the end on the threshold for dislocation mobility. Some stress level. You were asking question. What is a good threshold for dislocation mobility?
In fatigue, you mean?
Yeah, in fatigue. And some stage you say at the end of the manuscript, speaking about that,
85%.
What is the stress level and at which I start to have mobility. If I did read the work, okay. Do you think that there are really a threshold for that actually? Which is in that type of range?
So I think that these thresholds exist, especially in the systems that I'm working with. Similar behavior was also seen for, I think, 316L, where it was the threshold was 98% of the yield stress. So it was quite high. But for us, we saw
under what conditions?
I think it was your paper. I don't remember what's the name. Similar. Okay, so strain controlled, and so we also saw that in 316L.
I thought you make a bet. I have put $100 on the table with 50% of the yield stress. Yeah, I do the test. I'm sure I will have fatigue failure at some stage, which means that I've got irreversibility, which are starting very, 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 very low in terms of stress level. If you start to go to very low stress levels, but if you give time for the process to set up, you will have some.
But it's like a very long high cycle, very high cycle.
Very high cycle, but it means that the thresholds are just.
And the thresholds are, I think,
very low.
Subjective, so it depends on what.
I think it are not fully subjective, but let's see, back to statistics. In fact, if you have to start to include the statistic of jump of dislocation, and then when you do that, you start to have. So that's why my final point. Maybe we should start to think more about statistical distribution of quantities and start to, when we look at that threshold, I think it's not good vision. I think we can be much more mobile.
No, the reason actually, or sorry, I'm taking a long to answer as well. The reason that we wanted to show this is the instability or instability of these dendritic cells at this stage. So we were saying, like, despite having higher fatigue resistance, it is still important to see that there exists a threshold and the dendritic cells are not as stable. So also there's
very nice, but I mean in the Thank you very much.
Thank you.
Thank you. So now we are moving to Anissant from INSA Rouen. Please.
Thank you, Mr. President. So, firstly, I would like to thank for Clément and Williams for the invitation to review this very interesting work. Then, thank you also, Joshi, for the quality of the report, and I appreciate particularly the very, very clear theme and theme image. So for me, it's very difficult to obtain the same image. I also appreciate the result discussion performed for the all of the chapter in your report. So I have I start my question chapter by chapter. So firstly, I have a question concerning the chromium-rich precipitation. So you talk about the localization of this precipitation in the dendritic cellular walls. But I see also when I see the PDS analysis, I see in the wall of this cellular the nickel also. So the wall of the dendritic cellular is rich also in the not just in chromium but in nickel also. So can have you an idea about which phenomenon to have simultaneously the chromium and the nickel in the wall of dendritic cellular?
So, well, I think the reason that nickel also is there because simply nickel is 80% of the composition. So it has statistical advantage over chromium. So this is also one of the reasons. And hence we focused on more chromium because out of 20% we see the chromium rich oxides first of all, and also chromium has tendency towards tendency to forming oxides. The phenomena that could lead nickel and chromium both segregation, well, I think the answer will be complex, and it has to be associated with probably the solidification features of LPBF and how the liquid state and the mushy state are situated or are located in the solidification front. But other than that, I cannot think of any other phenomena.
Okay. Just it's not specified in the report. So the chemical composition of the powder and of your cast sample is exactly the same.
So no, I think we have some carbon in the cast nickel 20 chromium because it was also directly the samples were bought from one of the companies. So we have some carbon. So it is not exactly the same, but more or less the ratio is right.
Okay. Yeah. And you don't plate releasing heat treatment in your sample.
In LPBF, no.
In LPBF,
we do not. No. We just wanted to see the influence of as-built microstructure of LPBF.
Okay. So for you, this when you don't play the releasing heat treatment have an influence in making identification model because you identify the back stress and you can it's possible to have an influence or not?
Yes, certainly, because again we come back to residual stresses, because if it's not heat treated, then we should or we must have residual stresses in the as-built condition. So certainly it might influence dislocation behavior during tension. Different locations also have different, let's say, behavior of residual stresses. So certainly it might influence, but it will only be understood when we compare the heat treatment analysis and then compare it with the as-built. But yes, it might have an influence.
Okay. So for my question is concerning mix and cooking model. So if I understand all your identification, so all the identification of the model, it's from the macroscopic loading test. So you introduce in your model the microscopic parameter like grain size and cellular dendritic size, but the identification of the parameter is from macroscopic loading test. Yes or no?
So I'm not clear. Could you please clarify?
The identification of the parameter of the model.
Okay.
It's just from the macroscopic loading.
Yes,
test.
macroscopic. Yes. Yeah.
So in your model, you have microscopic parameter, but the identification is from just the macroscopic loading test.
Yes, it's an interesting.
Okay.
Yeah. Process.
And that you compare the result of your identification to the macroscopic tensile test. Yes.
Yes.
So for me, it's evident to obtain the same result because you are using this test to identify and you are validate your model with this test. So my question is, it is possible to validate the model with other observation. For example, in your report you have you have plotted the density dislocation density evolution from the model. Can you compare this result obtained from the model to experimental data, for example, to more validate this model?
Yes, certainly it is possible. It will be interesting. And in fact, here at JPM, engineer Renaud Henry works on micromechanical testing. And so it will be interesting if we could compare this micromechanical testing of LPBF samples and then compare it with the model and try to validate it. I think the issues or the differences which might occur in this comparison is probably size effects, because certainly if we compare micromechanical test and we are considering only one cellular structure or two cellular structures, then certainly if we have a grain boundary in the middle or not, so it might induce some more questions. But certainly it would be interesting to validate with the model.
Okay, so
but it will be, I think it will be subjective towards what microstructure we have in that micromechanical sample. So if we have a contribution of grain size, or we only take the contribution from cell size, the dislocation density, and so on.
Okay, so actually your model is just validated from the macroscopic tensile test, use it to identify the model. No?
Yes.
Yes. Okay. Finally, my question concerning this model. This model is empirical model or physical model finally? When you see...
So we started with empirical, but it has some physical interpretations.
Yeah.
So,
but maybe the interpretation of when you plot density evolution is obtained from the model, but the model you don't fit. It's the empirical, just empirical.
Yes.
So, for example, when you the value, you can comment qualitatively the result of this model. So the value of the dislocation density obtained from this model is compared to the result obtained in the literature. It's near or is
yes, it is quite similar to what we find in literature after deformation, the dislocation production rates, and what the final dislocation density might be predicted, which is predicted by the model. It quite matches the value that we get from literature. But yes, certainly, again, I will say that it is based on this model is clearly an empirical one, and also it explains whatever physical interpretation it has come from clearly the macroscopic testing. But the reason that I said that it has physical interpretations is we are trying to connect it with the microstructural characterization, and then this creates let's say physical understanding of this model. So
because I learned in the literature, big people thought that this model is a very physical model. So finally, the empirical model, but in the other scales. So it's empirical, but in microscopic scale.
Yeah.
Compared to, for example, Johnson-Cook model, it's the same, but difference at the the empirical system is applied in different scale.
Yeah.
Okay, so I have just one question in
Your last one?
last.
Or maybe two small ones?
Okay,
Last 5 ones.
The
Depends
cooler,
if you want to have.
yeah, chapter 3, one question, and the last chapter, one question. So 2 questions. The cooler rate is calculated from the dendritic cellular using a formula in page 86. So when I try to compare the cooling rate for different VOD energy, so the cooling rate for I can see that for the same laser powder, so 300, the cooling rate is multiplied by 5 when you just multiply the laser speed by 2. So I work in also in the simulation of this process. So you cannot obtain this result. So when you multiply the laser speed by 2, you cannot obtain the cooling rate multiplied by 5. Have you an interpretation of this difference?
Yeah, it's again, I feel it's the cooling rate that we calculated was based on Inconel, or the model which was supposed to be working for Inconel. So we tried to first of all take that directly in the model and compute. Secondly, we see that this is a very average, let's say, cooling rate, which might be for depending upon the average cell size, but we see that in realistic terms, certainly it will not be that average, and we will have a lot of different values. But I cannot. Probably you could clarify. Like I did not understand. You're multiplying the velocity with 5, and then
in the same laser power 300, you have 2 laser speed. You have 316 and 700.
Okay.
So you multiply just and the other all the parameter is the same. So you multiply just the laser speed.
No, but for
2.
our model, we have not. I mean, it does consider, or it can be calculated for different VEDs, but it has no relation with the VED formula or the power or the velocity.
Yeah, but
so it's probably just a again I would say correlation versus causation.
But you have your cooling rate is multiplied by 5 between when comparing the parameter and the cooling rate. When you multiply just this laser speed by 2, you multiply the cooling rate by 5.
Okay.
And when you try to simulate the model, you cannot obtain this result because you have a directly relation between laser speed and the cooling rate.
Okay.
So maybe if you have an explanation.
Interesting. So you're suggesting like maybe there. So to answer that, maybe it could be interesting to see if there is a direct relation between the dendritic size and velocity of the laser. And if we see that this relationship exists, I think then only we can try to answer the question which was asked by you. So until I think we can do that, until we do that experiment, I think I will still think that it is again causation with correlation. But if I have to answer for the physical aspect, I feel yes, I can agree that increasing or multiplying the laser velocity by 2. Certainly, it will have a lot of influence on the heat which is input, and also it might generate some balling or weld bead effects. So the fabrication might have an issue. So maybe the simulation is not considering those issues, and that's the reason we have different, or the simulation has different values. I'm not sure. I mean, just simply multiplying the velocity, I think we cannot directly take a physical interpretation, because we don't know how multiplying velocity, if that VED will generate a dense material. So I think unless we have the data, it's very difficult to answer that.
Okay. And my last question is a very, very small question. You don't talk about the strain rate of your fatigue test. So it's the same strain rate because all your test is the strain control test. So you apply the same strain rate for all the tests for high cycle fatigue, low cycle, medium cycle fatigue test. You have the same strain rate or not?
I believe so. We have used the same strain rate.
So you apply a strain rate or you apply frequency?
No, we apply frequency. So
And,
yeah, no, that will be different. Yeah, no, right. In that case, sorry, we don't apply strain rate. Yeah, so we just go to the strain level with changing the frequency.
So you have the
we
same.
have different.
It's the sinus.
I would say so.
So when you have
But
the
the
same
frequency is
frequency
different.
or the
No, the different frequencies.
different.
Yes, yeah,
so
different.
the same strain rate. So,
Sinus.
okay. So thank you for your work and it's very, very interesting. Thank you.
Thank you. So now I'll give myself some time and I will be very careful with my time as well. Considering that I must manage myself. So if we can go to slide 47, we're not so far from that one. The good question. Good thing is you have already many questions on the model, and I'm not going to ask you questions on the model. But I will focus on other things then. Yeah, you're having these oxides particles, and you don't say much about them. You notice they were there, but well, it looks to me when I look at what's in your manuscript that they're changing size when you're changing the VDT. Is that correct?
Yes, they will change sizes. Yes,
agree with that?
yes.
I was wondering if that could affect the mechanical properties. Like, I wouldn't expect them to have so much on-one effect, right? But I have more in mind elongation, for example. The reason why I'm saying that is because it's quite well known that when the size of a particle increases, the chances of leading to damage is higher. And so I would expect it to have an effect on ductility, maybe. Did you notice any of that? Can you comment on that?
So first of all, yes, we can see that the ductilities change, but again, we have not considered ductility in this PhD. The only aspect for till
But
necking.
it's changing in what direction? Is it like influenced, you think, by these chromium particles? By their size increasing with VD?
The thing is, the ductility in general with increasing VD increases, but the reason for that is because the dislocation or the dislocation size, the grain size, everything is
because
increasing.
the strength is decreasing.
Yes,
right?
the strength is decreasing as well.
Yeah.
So it has a combined effect. But if comparison could be made that everything is same and we have difference in the oxide sizes, then I think clearly the ductility will be a function of oxide sizes. Yes.
Yeah, but if you have a lower strength, you're totally right. If you have a lower strength, of course, the indication of damage will come in later. So that of course. So probably this should be like contracting. So you have like something that's a similar damage conditions, like they might similar utilities. I'm not talking about the strain at neck. I'm really talking about the fracture strain. But I saw in one of your slides that you did measure it. Did you measure it for all the?
No, it's only for 62 joules per millimeter cube. So the whole PhD was supposed to be only on this one.
Yeah. Well,
Yeah, one. And then the reason that we found this model works and it's interesting and it's giving us results. The next question we asked in the final year of my PhD is what happens if we use different process parameters?
right.
So yeah.
Well, interesting. Thank you.